Hello and welcome to our physical sciences lesson. My name is Temba. Today we are going to focus our attention on investigating terminal potential difference, which has got to do with electric circuit. So it's within the broader, knowledge area of electricity and magnetism, right? Then in terms of the overview, so this is in the context of electric circuits. We're going to look at EMF. We'll also look at different types of volts within a circuit, but of particular focus to us or attention or our interest is terminal voltage. So there are a whole lot of concepts and quantities involved in as far as terminal voltage is concerned. Right. Okay. So the thought that's going to guide our discussion for today is as follows. Have you ever thought about what happens to the energy, provided by the battery in a circuit? Right. Immediately you talk of energy, you are tempted to obviously refer to the law of conservation of energy that talks about the energy conversion, the fact that energy cannot be created or destroyed. So it's very important for us to also appreciate that a circuit has a lot to do with energy. So we want to understand or arrive or discover what happens exactly to the energy of the battery in as far as the circuit is concerned. Right. So terminology, very, very important. This is another part that we also have to, emphasize. When we talk about definitions, the examination guideline is our point of reference in as far as what is acceptable, in an examination when it comes to definitions. Definitions are all or nothing, so you need to pay careful attention to the keywords, and the keywords must also be used in the correct context. So what are some of the keywords? The keywords that we'll use a lot will be terminal voltage, as well as EMF. So these are the two key terms, right? Right. Think about this. What does the voltmeter reading tell us about the battery or a source? Voltmeter is an instrument, a device. So this is a device that we use. So there's a difference between voltmeter and voltage. So voltage is actually the quantity, So voltage is the quantity, that can be measured. So what is used to measure this quantity is a device called a voltmeter. So the question is, what does the voltmeter reading tell us about the battery or the source? Right. Now we're going to construct a simple circuit. What are some of the things or the most important things? You need a source of energy, which is a 12-volt battery in this case, right? We'll also have an open switch. Pay attention to that, open switch, right? Also, we'll need an ammeter as well as a voltmeter. So this one will measure voltage, while the ammeter is a device that measures current, right? So these are some of the things that we already know. And what else? We'll also need a light bulb with a 6 ohm resistance. So a light bulb is a resistor in many ways. Now let's set up our circuit and see exactly what is happening, Right, so here is our circuit, right? So in this circuit, we've got a 12-volt battery, There we are. What else do we have? We have an open switch. We also have a light bulb with a resistance of 6 ohms, right? So we are going to set up this circuit and try to use it in our investigation, right? So we already have that circuit. Now let's go back to our slide. So here is a circuit. The intention of setting up this circuit is to try and measure. So measuring is a very important skill in science, but what exactly are we measuring? We're measuring potential difference or voltage, across the battery, right? That's what we're going to do. So let's go to our simulation where we already have our circuit, right? So in this circuit, we are going to measure voltage using a voltmeter, right? Take note, the switch is open, so across the battery, we'll connect the voltmeter and take the readings. Okay, why do we use the voltmeter? Actually, we connect the voltmeter between 2 points. It's because we are measuring potential difference between the 2 points. In this case, it's across the battery. So the reading that we obtain is 12 volts. What about the current reading? It's 0. Take note of that. The bulb is not glowing. So if we can go back to our slides, we are saying, okay, as far as measuring the potential difference or the voltage, the voltmeter reading is 12 volts. Okay, we obtained that. And then the ammeter reading is 0 amperes. There is no current in the circuit. We want to appreciate that. And then we're also saying that the potential difference across the battery is 12 volts, which is the source, and the light bulb is not glowing. Okay, right. Now, what is potential difference as a physical quantity? It is the work done per coulomb of charge. So W is work done, okay, or energy, right? Work is energy and energy is work. Okay, this is measured in joules, while Q stands for charge. So by definition, again, charge is in coulombs, right? So by definition, we're saying potential difference is the work done per coulomb of charge. In other words, when we've got 1 volt of potential difference, it means that there is a joule of work done for every coulomb of charge, which gives us this mathematical equation to say a volt is equals to a joule per coulomb, right? Okay, now what does 12 volts mean? Now, if we know that 1 volt is equals to 1 joule of energy or work done for every coulomb of charge, then it means 12 volts is also equals to 12 joules of work done for every coulomb of charge. That's what, so equivalently, if you have got what, 24 volts, it means that there is 24 joules of work done for every coulomb of charge. And when we say per unit charge, we're talking about 1 coulomb of charge as the SI unit, right? Okay, and then we are happy with the 12 volts is equals to 12 joules per coulomb of charge. Right, now let's look at the micro view of potential energy in an electric circuit. So we're saying a coulomb of charge, which is 1 coulomb, that is at a 0 reference point, which is called the ground. Okay, so we're going to use this as because we talk about the difference between 2 points. Now, then if we have got 12 joules, it means a coulomb of charge, it carries 12 joules. So a coulomb of charge, so if you're saying V is equals to W over Q, then if we're saying it's 12 volts, then we're saying V is equals to 12 joules divided by 1 coulomb, which gives us V of what? 12 volts. Okay, that's what we are simply saying. All right. Okay, so where we've got a blue one, it says that there's 12 joules for every coulomb of charge. Right. Now, so across the battery, the potential difference is between 0 and 12 joules is that we've got 12 joules for every coulomb of charge across the battery, because the voltmeter has been connected across the battery. So when there is no current in this circuit, we want to recognize that the potential difference, that 12 volts, is a result of the 12 volt is the potential difference between 12 joules per coulomb less 0 joule per coulomb. Right, so this gives us what? 12 joules per coulomb as potential difference. Right, okay, now in conclusion, for an open circuit, the terminal voltage across the battery is 12 volts. There is no current flowing, which means there is no work done in the circuit. Then that's why we register a 0 ampere of current from that ammeter. Right, so the potential difference across the light bulb is 0 volts. Okay, so the implication or the meaning for that is that there is no work done, okay, by charges in the circuit, since there is no charge that is moving. The no charge moving suggests that current in the circuit is equals to 0 amperes. Right, so this is one of the very important things. And beyond that, we are able to arrive at what exactly EMF is. So EMF, by definition, the symbol is E, is the maximum energy, okay, supplied by the battery or the source per coulomb of charge. And when we talk about maximum energy, we can say also maximum work, right? So this has to do with maximum work, okay? So this also comes from the fact that, so EMF is measured in volts, right? We appreciate that because we are saying V is equals to W over Q. So the maximum energy that a battery can supply for every coulomb of charge is actually our EMF. So EMF is some form of voltage or potential difference across the battery. And then when do we obtain the EMF reading? When there is no current in the circuit, we are able to get the maximum energy that the battery can supply. Right, so the EMF reading of a battery in a circuit is obtained by connecting a voltmeter across the ends of a battery in an open circuit. So this has to do with EMF reading. It's definitely not the EMF as a quantity. How we obtain the EMF reading, or what's an indication of what our EMF is, has a lot to do with the open circuit. So that's when we can be able to get the maximum reading of voltage, right, across the battery. So an EMF of 12 volts is defined as a total of 12 joules, which is a maximum potential energy supplied by the battery per coulomb of charge, right? So that's in as far as EMF is concerned. We'll take a short break for now. When we come back, we'll look at a typical closed circuit within the same setup. Let's take a short breather for now. Welcome back to our session. We're still investigating terminal voltage, but now we'll focus our attention on a closed circuit and try to take readings across the battery and see if there are any changes and talk the science behind that. Right. So we are measuring voltage once again across the battery, but we're going to construct a same circuit. We're using a 12-volt battery, but emphasis now, we're going to close the switch and make our observation, okay? And then talk the science behind that. And then also we'll use the ammeter and voltmeter to take readings. We'll still use our 6-ohm light bulb in our circuit. So this is the setup. Now let's go straight to our simulation and see what happens. Right. So if you look at the voltage across the battery is 12 volts, okay? This is actually our EMF reading. So this is the maximum energy of 12 volts for every coulomb of charge. Right, so the switch is open, there's zero current. You can also confirm the resistance of the light bulb is 6 ohms. Right, so what we're going to do now, we're going to close the switch and see what happens. The moment we close the switch, we realize that there's a drop in the reading of voltage across the battery, while now there's a current of 1.5 amperes, right? Now, we will go back to our slide and talk the science behind that. Right, so this is basically what we obtained from that setup when we closed the switch. Right, okay, what does this mean? The voltmeter reading now, when the switch is closed, emphasis is on that, okay, that's a closed circuit. The reading has dropped from 12 to 9 volts. Now, and also the current reading, when we closed the switch, it changed from 0 to 1.5 amperes. And also, what is it that we observe? The bulb is glowing. Right. Okay. Now, what conclusions can we draw from these observations? Now, there is a terminal voltage of 9 volts across the battery while the switch is closed. Okay. Then there's a current of 1.5. The potential difference across the light bulb it's actually something also that we can measure. We can go back to our simulation and measure the potential difference across the light bulb, which is the same as across the battery. Right, okay. So we will go back to that, okay. And then we're saying the work done by the charges in the circuit in moving through the light bulb in the external circuit, there is work that is done. While when the switch was closed, work was not done. So now the difference is that work is done. Right. Okay, and then let's look at the micro view, which explains the science behind these observations. Now, the 0 joule per coulomb of charge is something that we would have obtained when the switch was open between any point except across the battery. But the potential difference across the battery, we recognize that it was 12 joules, right? Now, in this case, it becomes 9 because we've closed the switch, and then there is current in the circuit. Now, the terminal potential difference is 9 volts, right? Okay? And then what exactly is happening in terms of potential difference? You realize that the potential difference across the battery is 9 volts, which comes from 12 minus 3, right? And anyway, along the conductor, there's a potential difference of 12 between any 2 points, right? Now, this suggests that the wire or the conducting wires offers 0 resistance. Similarly, the ammeter, across the ammeter, there's a potential difference of 0. So it means there is 0 resistance on the ammeter. So we can safely say or conclude or assume that the ammeter has negligible resistance. But what's the voltage terminal difference, potential difference across the light bulb? We still get the 9 volts that we managed to actually measure. Right. Now, let's compare the 2 circuits, the open one and the closed one. Now, the terminal potential difference when the switch was open was 12 volts, all right, which is the maximum. While we closed the switch, the value of the terminal potential difference dropped to 9 volts. That's very, very important. And also, the ammeter reading in this case is equals to 0 when the switch is open. When we close, now there is current in the circuit of 1.5 amperes. Right, these are just observations that we made from the setup in the simulation. Right, so in an open circuit, we've got terminal voltage of 12 volts, which you obtained, while the closed circuit is 9 volts. Now, the big question that we have to ask ourselves, what happens to the lost volts? Right, the word lost is put in those characters. Why? Because we know that voltage has to do with energy. Okay, and we know that energy cannot be created or destroyed. But then how do we account for these lost volts? Right, so where was more work done by the charges in the closed circuit? Because in the closed circuit, there was a difference, a drop in the reading by 3 volts. Right, now what are we saying? A battery has some internal resistance. So this is something. Now, there is some internal resistance in the battery. As you can see, that is inside the battery. So there is some small resistance inside the battery. Take note of the symbol of the internal resistance, small letter R. So what does that mean? It means work is done, or energy inside the battery is converted to heat as the battery does work in terms of per coulomb of charge. So when a battery is connected to a circuit, energy is dissipated because of its internal resistance. So not all the maximum energy that the battery can provide is turned into electrical energy, but some of it is converted to heat energy, right? So a relatively small amount of electrical energy is converted to heat. So this would think of it as lost because it doesn't become electrical energy. Right, so the terminal voltage in an open circuit, okay? Now the terminal voltage for an open circuit is called the EMF of the battery. This was the 12 volts in this case that we managed to record. So the EMF of the battery is the actually maximum energy stored per coulomb of charge. So the EMF of the battery does not change, it stays the same, right? But then the terminal voltage for a closed circuit, now we're looking at the closed circuit, is the potential difference of the external circuit. So that 9 volts is actually the terminal voltage of the external circuit. Okay, so stored energy from the battery is converted into heat inside the battery and light when the charges are actually moving through the resistors or the light bulbs of the circuit. Okay, so the 3 volts is inside the battery, then the 9 is actually outside the circuit, which has to do with the resistance of the light bulb. So V external or external voltage is the potential difference of the external circuit. So the external circuit, we're talking about your conducting wires as well as the light bulb, right? Okay, so lost volts, okay, and remember this is lost in the sense that it's not converted to electrical energy. So the difference between EMF and V external is actually the lost volts. So inside the battery, there is an internal resistance of R, which can change depending on the type of source that is used. So stored electrical energy is converted to heat when charges move through the battery. So what about internal voltage? This is the potential difference of the internal circuit due to the internal resistance of the battery, right? Okay, so when we talk about the battery and the resistors in this in the external circuit, we know that the internal resistance of the battery and that of the light bulb is actually in series. So whatever current passes through the battery will pass through the light bulb in this case. So resistors in series are potential dividers. Now this takes us back to some of the stuff that we know. When we have got two resistors that are connected in series, we know that potential difference is divided, okay? But then the amount of current that passes through the battery with its internal resistance will be the same as the current that goes through the light bulb in this case, because the internal resistance of the battery as well as that of the light bulb are actually connected in series. So they receive the same amount of current, okay? Right. So in other words, we are saying that this maximum potential difference, which is the EMF, is split between the external circuit and the internal circuit, which is the battery in this case. Right. So in short, we are simply saying that EMF becomes the maximum, okay, voltage. But this maximum voltage is actually for the battery, right? Okay, so in other words, we had 12 volts of EMF of 12 volts, right? And then we found out that the voltage that goes externally to the light bulb, we measured it across the light bulb, which we can even go on to confirm it. It's 9 volts, as you can see from the simulation, right? Okay, now, so the external is 9 volts. So how much was lost, or the drop? The drop was due to the internal resistance. So the voltage due to the internal resistance of the battery is 3 volts. So in other words, we can simply say 12 volts is equals to 9 volts plus 3 volts. Okay, so that becomes our E. That's our V external. Okay, and then obviously that's our V internal. Okay, so these are actually our potential dividers, as we would like to refer to it. Right. Welcome back to our session. We're still investigating terminal potential difference. Right, let's look at the Ohm's law in terms of how it fits into the context of circuit in as far as, you know, terminal potential difference is concerned. Right, so we want to look at the Ohm's law, okay, because we are dealing with circuits that talks about the relationship that exists between potential difference and current. But before we do that, let's remind ourselves of what the Ohm's law says. Right, at this point in time, I also want to emphasize the fact that this is a common question that is asked in terms of remembering skills. You know, the question may come and say, state Ohm's law in words. So you must be able to state the Ohm's law. Very, very important are the key terms that you must include in the definition, as well as you must also use those keywords in the correct context. So this has a lot to do with remembering, which is all or nothing. Right, so what does the Ohm's law say? It states that the current passing through, you know, a conductor is directly proportional to the potential difference, or the voltage across the ends of the conductor if temperature remains constant. So what we have underlined is what is very important, or what would refer to as the key terms in as far as the Ohm's law. Right, so the Ohm's law equation says R is equals to V over I. So sometimes we may represent it in this way. So the formula sheet actually provides us with the Ohm's law. Right, So we must be able to copy it correctly and use it where appropriate. So, or we can talk of in terms of the potential difference and say V is equals to the product of current and resistance. So it's still the same equation, but expressed, you know, in a different form, right? Okay, so terminal is, in as far as terminal potential, terminal voltage and resistance are concerned, we know that the battery has an EMF of E connected to the external circuit, which has some resistance. So this resistance is for the external circuit. But do not forget, the battery in itself has got its own internal resistance, right, which is R. So the external resistance of the circuit in the case of the simulation was the light bulb, would represent that external resistance with capital letter R. So in terms of notation, the capital letter or uppercase R represents the external resistance. It could be a bulb, it could be anything, right? And then with the battery, the internal resistance is denoted by a small letter R, right? Okay. And then what else did we manage to realize? This the difference in terms of, you know, the measurements. We knew that when we connected the voltmeter across the battery, when the switch was open, we got a voltage of 12 volts, right? And a current of 0 amperes. That was for the open switch. But for the closed circuit or closed switch, we got a voltage across the battery, right? And we must emphasize on that, of 9 volts. And the current was now 1.5 amperes. So there's no current in the open circuit, while there's 1.5 amperes of current in the closed circuit. But the difference is that also the light bulb is glowing in a closed circuit, while it is not in the open circuit, right? Okay, so we are happy with those reading. So we are saying the battery is not doing work, any work in moving charges in the external circuit or in the internal circuit. So there is 0 current. This statement suggests that current in an open circuit is equals to 0 amperes, right? Okay, and then in a closed circuit, what happened? We know that our EMF now, which is our maximum, in this case was 12 volts. But when we close the switch, as it is shown in the circuit alongside, we obtained a V external of 9 volts. So what happens here, if we close the switch and measure the voltage across the battery, this gives us the external voltage, which is equals to 9 volt. Now, the lost voltage is actually 12 minus 9. So in other words, V lost, okay, or V internal, all right, sometimes we would refer to as V internal, is actually equals to EMF less V external, okay, which is what gives us the lost volts of 3 volts. Okay, so our V internal in this case is equals to 3 volts, right? Okay, and then when the switch was closed, we also identified that the 9 volts is divided. Okay, as actually the 12 volts, which is the maximum, is divided between the external voltage and the internal voltage, which is why we are saying that 12 is equals to 9 plus 3. Okay, this is in terms of voltage, right? But what do we know? We know that according to Ohm's law, we know that V is equals to the product of current and resistance. This is with respect to the external circuit. But in as far as the internal circuit, we know that V, so this is external, okay? So V internal will be then equals to current multiplied by the internal resistance, right? So hence it gives us that equation, okay? We can express this equation by applying the Ohm's law, right? Okay, then when we do that, we can also say, right, we are able to say, okay, if in this case, this is for external voltage and that is for internal voltage, we can say current is the common factor here. We can talk about this in terms of, you know, the product of current and resistance. And if you look at it, this is like V is equals to I multiplied by R, because that is resistance, this is current, that's voltage. So this, we're still applying the Ohm's law when we say E is equals to I R plus R, okay? So this is actually the resistance of the circuit, both you know, of the battery as well as you know, the external circuit in this case, which is the bulb, right? So these are these are variations of, the EMF equation, right? That's how we would actually apply it. So whether you choose to look at it in terms of E is equals to V external, okay, plus V internal. It's the same as saying V is equals to I multiplied by R plus R. But why is I a common factor? Because the current that goes through the battery, okay, we're talking in terms of internal resistance, will be the same as which goes through the external circuit, in this case, which is the light bulb, because these are actually in series, right? That's why we talk about the sum of the two, okay? So in as far as that equation is concerned, I think it's very, very clear. So when the switch is closed, we can apply the Ohm's law. So if you think of the importance of the Ohm's law, is that we need to understand the Ohm's law so that we can correctly apply it. And then why do we add the resistance of the light bulb to that of the battery, which is the internal resistance? It's simple. We're talking about resistors in series. Okay, so if two resistors are connected in series, their effective or equivalent resistance is the sum of the two, which gives us the big R plus the small r, okay? And also, they receive the same amount of current. That's why we managed to factor out the current, because it's the same amount of current in a series circuit, right? All right, so we are simply saying the equation E is equals to I R plus small letter r is actually an application of the Ohm's law, which is V is equals to I multiplied by R, right? So these are some of the very important concepts in as far as, the application of the Ohm's law. Now, we'll take a short break for now. When we come back, we'll look at typical circuit problems and see how we work around, your internal resistance, your EMF, your current. So we'll try and make use and apply this equation in solving problems. Let's take a short break for now. Welcome back to our session. Now we will focus our attention on circuit problems, but of importance to us is also to try and understand how we approach these circuit problems, but we'll try and use the EMF equation to see how exactly we apply it in as far as circuit problems are concerned, right? So we also need to remind ourselves that the Ohm's law becomes very, very important, and also because it's a circuit, we could either have a series or parallel, or a combination of series and parallel circuit, right? Okay, so questions may give EMF. So EMF might be given, but then say internal resistance can be ignored or is negligible. So in most cases, or in some cases, if we ignore internal resistance, we'll know that the EMF will equals to external voltage. But however, if we look at it in terms of the EMF in the circuit, which does not change, we are saying that the current outside the battery, which is the main or the total current, is actually the same as inside the battery, all right? Okay, now, given the EMF and the total current, we are also able to find the internal resistance of a battery. Now, in short, what we are saying, in as far as internal resistance is concerned, in a circuit, you can either be given internal resistance or not given. Either of the two, it's not a train smash. As long as we are able to identify some of the quantities that we have, then we are able to make use of the EMF equation, right? So if we are given the EMF and the internal resistance, we are also able to find the total current, right? Now, here is a practical example. Consider the circuit shown, okay? The internals of the resistance of the battery cannot be ignored. So let's interpret that. It's a very important piece of information. We are told that we are not going to ignore the internal resistance of the battery. What does that tell us? It tells us that the internal resistance of the battery is not negligible. We are going to take into account the internal resistance of the battery. Very, very important. Right. So here is the circuit that is given. right? If we can look at it, it says with the switch open, okay, you can realize that even in the given circuit, the switch is open, right? The reading on V1 is 9 volts, right? What is this reading of V1? With an open switch, what does V1 actually measure? V1 is equals to 9 volts. What does that tell us? It tells us that E is equals to what? V1, which is equals to 9 volts, right? So with the switch open, the potential difference across the ends of the battery, it actually gives us the EMF reading. So V1 measures EMF with the switch open, right? Okay, now we are also told that when the switch is closed, the ammeter reads 0.4 amperes. So when we close the switch, we have got an ammeter reading of what? 0.4 amperes. Now we are supposed to calculate the internal resistance of the battery, right? Okay. Now, what are we saying? We are saying that the current that goes through the 5 ohm resistor, in this case, which is connected in parallel with the other 5 ohm resistor, is equals to what? 0.4 amperes. So if this is 0.4 amperes, what will be the current that goes through the other 5 ohm resistor? What is very, very important here is that the two resistors are actually connected in parallel. And these are identical in the sense that they've got the same amount of resistance. So whatever current goes to the 5 ohm, it will be the same amount of current that would go through the other 5 ohm. So current will be equally split. Here we've got another 0.4 amperes. So what is the total current in the circuit? We can choose to look at it that way. Or we can use the equation, right, to find R, okay, which is the total R. Now, if we are to say, okay, if 0.4 goes through, let's call this the 5 ohm, let's call it R2, and let's call this R3, let's call that R1, and let's call that R4. So the total current in the circuit, in this case, we realize that total current is equals to 0.4 times 2, which is 0.8 amperes, right? But now let's go via the route of calculating using the EMF equation. Okay, we can find the total resistance, okay, of the circuit, which is first of all we need to find the R parallel, okay, which is the 2. So R parallel in this case is equals to product over sum. Product is R2 multiplied by R3 divided by the sum R2 plus R3, right? So if you do your maths, that gives you 5 times 5, which is 25, divided by 10, okay, which is 2.5 ohms, right? 2.5 ohms, right? This is R parallel. So the total resistance in this case will give us what? 2.5, which is in series with the 6 ohms, which is in series with the 2 ohms, right? So the total resistance that we get here is going to be, what do we have? 6 plus 2, which is 8. 8 plus 2.5, which is 10.5 ohms. But actually, we want to appreciate that this is R external, which is 10.5 ohms, right? But we are interested in calculating the internal resistance. Right, but now we have the total current in the circuit. We are able to do that, right? Okay, so if we go the route of saying E is equals to I, okay, R plus R, okay, we are able to say, okay, when that switch was, EMF is 9 volts. When the switch was open, okay, we know that the total current in the circuit, in this case, this is the current for the 5 ohms. So the total current, that's the catch, right? If 0.4 goes there, right, another 0.4, so we'll have 0.8, right? Then the total resistance, we've managed to calculate it as 10.5, right? Then we are able to get the small r, right? So what is our value there? We can quickly go to our calculator, but before we do that, we are able to say this is the same as 9 divided by 0.8, right? Minus 10.5, right? 10.5, this gives us our internal resistance. So we can go to our calculator and say Okay, this is 9 divided by 0.8, which is the total current in the circuit, right? This less 10.5. Okay, what does this give us? It gives us a value of 0.75. So our internal resistance of this circuit is equals to, just to confirm that value, 0.75, all right? 0.75 ohms. So this is a very small resistance that the battery actually has, right? So we're good with that. Right, now we have another circuit problem. In this case, we're also given the EMF of 12 volts and an internal resistance of 1.5. So what's different in this scenario, if we compare it to the earlier one? In the first case, we had to arrive to say, okay, we have the EMF, even though it was not given directly. Needed to appreciate that the switch is open, so the potential difference across the battery is actually the EMF reading. So in this case, we're given the EMF, okay? We are also given the internal resistance, right, which is 1.5. So we're saying E is equals to 12 volts in this circuit. Internal resistance is equals to 1.5 ohms, right? This is what is given, okay? Right, so they want us to determine the current through the 25 ohm resistor, right? So in other words, we are looking for current that goes through the 25 ohm resistor, right? Let me just correct that, okay? So we want the current that goes through the 25 ohm resistor. We also, if we look at the circuit, right, all the current passes through the 25 ohm resistor. So this is like the total current of the circuit, which is what we are looking for. All right? So that's our interpretation. So we want to determine that current. All right? Now, first of all, we need to look at the effective resistance of this parallel combination, which is actually in series with the 25. So again, we can use the formula, the R parallel is equals to, let's say this is R1, that is R2, and then that is R3, right? We can say product over sum, which is applicable only for two resistors, which is R2 multiplied by R3 divided by the sum of those, which is R2 plus R3. Okay, so if we say product, there is 60 by 60, right? Divided by the sum, 60 by 60, which is actually 120. So what is our R parallel? Okay, our R parallel, we can simply obtain that 60 by 60. These are identical resistors once again, okay, because they've got the same resistance whose sum is 120 ohms, right? So that gives us 30, right? There's something very interesting. You'd realize that when you have two resistors connected in parallel, their effective or combined resistance is actually lesser than the smallest resistor. So the smallest resistor in this case is 60 ohms. So the effective resistance must be less than 60 ohms, okay? Now, which is 30 in this case, which is actually half of that. So this is 30 ohms. So total resistance, R in general, which is the total resistance in the external circuit, is equals to R parallel, right, plus R1, okay? R1, which is our 25 ohms. In this case, which is 30 plus 25, that gives us 55 ohms, okay? So that's our total resistance. But remember, we want the current, right? Okay, so if that's the case, this is what we have, okay? So if we want the current, we are saying this total resistance is 55 ohms. We've managed to obtain that, okay? So the equation says E is equals to I, okay, which is the total current, external resistance, which is in series with the internal resistance of the battery. So we have all these values except for the current that goes through 25 ohms, which is the total current, okay? So our E is 12, right? We're looking for the current. What do we have there? We've got 55, okay, plus given the internal resistance, which is 1.5, okay? Right, then if we are looking for I, in this case, our total current is gonna be 12 divided by the sum of those 55 plus 1.5 is 56,5. Okay, then we can say then the current which goes through the 25 ohm resistor. If we go to the calculator, what does it give us? We have got 12, okay, divided by 56.5. Okay, this gives us a current of 0.21, right? The current is 0.21 ohms. Right. Now, this is we can say, therefore, this is the current that goes through 25 ohms, which is actually the total current in the circuit. Right. Okay. So the value of current is 0.21 amperes. It should be to 2 decimal places unless or otherwise specified. So the current is 0.21 amperes. So this is the total current in the circuit, which is the same as the current that goes through the 25 ohm resistor, because that's what the question required of us. Right. So having said that, I think it's very important to say these are just examples that we've used, and with more and more practice you become very comfortable around working with circuit problems, and the attitude is that you always treat each scenario as unique. But as you do more and more practice, you get to realize, okay, there is something that's common about them, but each question must be treated, as unique as possible. So these are some of the simple examples, but the idea is how you approach the circuit problems. Having said that, that's all the time we had for today. It's bye-bye for now.